Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video introduces the concept of goodness of fit hypothesis testing and describes the process for conducting such a test. Let's get started. So, goodness of fit hypothesis testing uses what's called a one-way frequency table. And this is basically just sample data consisting of observed frequency counts arranged in a single row or column. So essentially, a one-way frequency table is a frequency distribution table that we've seen in previous mini lectures. Goodness of fit simply means that the sample data we see in our frequency distribution agrees with some other particular distribution. So the two distributions are matching, okay? The particular distribution we match it with could be, we could test for anything, really. So we could look at the normal distribution, the student t distribution, the uniform distribution, the F distribution, the chi-square distribution, any distribution, okay, we can compare it up with. So, that's just what that is, okay? We're going to use a hypothesis test for the claim that the observed frequency counts agree with the claim distribution. So in other words, we're going to test the claim that the two match up. And that's what the goodness of fit test pretty much is, okay? A hypothesis test conducted to determine whether our frequency table agrees with some specific distribution. We conduct the test by claiming the sample data in a one-way frequency table fits a specified distribution, and then we complete our hypothesis test, which is what we're going to describe here. Our null hypothesis will be that everything matches up, okay? Remember, the null hypothesis is by definition a statement of equality. So in this instance, equality means the distributions are matching up. They're the same. They match up to each other. Our alternative hypothesis is pretty much going to be set. It's going to be that the frequency counts don't agree with the claim distribution. So our different distributions, there's going to be some difference somewhere, something that's statistically significant, okay? Some special notation to keep in mind for goodness of fit tests. Capital letter O is used to represent the observed frequency of an outcome. We get that from the sample data because that's what we observe. Capital letter E is the expected frequency of an outcome, and we find that by assuming that the distribution is as it's claimed to be. Lowercase letter k is the number of different categories that we have in our sample data. Lowercase letter n is the sample size. So this is the sample size across all the categories put together. It's the total number of trials, total number of observed sample values. Lowercase letter p is the probability that a sample falls within a particular category in our data. There's some requirements we need to run through to make sure that we can actually use the test, because the test is resting on certain assumptions. The first assumption we're making is that the data have been randomly selected. Next, we assume the sample data consists of frequency counts for each of the different categories. So if we have actual raw data, we need to make a frequency distribution first. We need to make that summary table of the frequency counts first before we can run the test. Third, for each category, the expected frequency is at least 5. Notice here how we're talking about the expected frequency, not the observed frequency. The observed frequency, okay, can be whatever it is, okay? Because that's what we're looking into the real world and figuring out what do we observe. So there's no restriction on what we're observing, because it's just going to be whatever it is. But the expected frequency that comes out, so in order to match it to a specified distribution, we have to expect to get a frequency of at least 5 for each category. if we're not going to get at least 5 from the expected frequency, then the statistics behind the scenes just don't work out to where you can actually say with certainty whether it's a match or not. Keep in mind, our hypothesis test for goodness of fit will always be a one-tailed test on the right. So we're always going to have a right-tailed test. Okay? Where here we have our region of rejection defined as the test statistic bounding that tail, and then the area is going to be the p-value. Our test statistic is going to be calculated with this equation here. So we're going to take the sum of the quantity of the differences, of the square of the differences of the observed and the expected frequencies divided by the expected frequency. We obtain p-values either with technology or with a chi-square distribution table, since you see that our test statistic is a chi-squared statistic. So we can do this either way, and typically you're not even going to bother calculating this. You're just going to go ahead and just use the technology there in StatCrunch to get your test statistic for you. Of critical values, we can get the same way. We just go to our table or technology to get the critical values out. Remember, k minus 1 degrees of freedom, where k is the number of categories in our data set. And then, once we've got the test statistic, the critical value, we've got what we need to run the hypothesis test. Alternatively, the p-value we compare with the significance level. Either way you look at it, once we get to this point, everything follows out exactly as we've done hypothesis testing before. So the rest of the test is exactly as we've seen hypothesis testing go. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.